And now we'll move to our next speaker, Dhaka Sapkota. And Dhaka will give a talk on gravity scaling of the cratering mechanism by a cold, turbulent subsonic jet. Dhaka, please, you have 10 minutes.
Hi, everyone. I hope all of you can hear me well. I will again be talking about the cratering mechanism, just like Douglas did, but this time I will be talking about based on some experiment that were done in the past, and then I'll try to connect all the physics behind the cratering, the erosions to the gravity. And my co-investigator on this are Phil Metzger and Marla Philippe from Florida Space Institute at University of Florida. Going into the experiment, I'll try to set up some relevance to the work, and the relevance comes from the physical state of the space. As we heard many times in this conference, the surfaces of the moon and Mars have a dusty layer of granular regolith. The engine exhaust from the landing spacecraft blows away the regolith, and then it changes the environment physically, chemically to the long term. It can also sandblast the hardware within reach. And then as Douglas also mentioned, the particles can even reach to the escape velocity. So it's really important to understand the erosion during the landing. And then for this, we use the experiment that were performed quite a bit time ago, about 10 years. And then, but the data were never analyzed. So we went back and then started to do the analysis. The instrument was called the HUSH, the handheld observations of the scour holes. As you can see on the top right, it's an enclosed transparent chamber with a sand bed inside. The fan circulates the air within the chamber going through the flow meter. The nozzle is divided, it's splitted by a bevel wall so that we only see only the 50% of the gas will make the crater. So if you look at the front view from the below, we see the vertical dissections of the crater, which can be recorded. Those experiments were recorded as a video file. Different variations of the variables were used, such as jet speed, different sand types, and the gravity levels. We analyzed the data and present with some observational and analytical results here. Going to the observations, there are a few distinct erosion patterns that we observed, that we call them a bearing capacity failure. This is the term widely used in the engineering, when the stagnant pressure of the jet breaks into the sand. This happens to during the beginning or the intermediate stage of the cratering. Then after, we observed what we call the diffusion-driven shearing. It happens during the intermediate to the final stage of the cratering. The gas diffuses through the soil, induces the drag force throughout the bulk of the soil. And then at the end of the cratering, we observe what we call the repose erosions. It starts from the intermediate stage and goes to the final stage. The exiting gas from the crater soaks up the sand from the top of the crater and makes a conical top. On the right, here's a video I will play. It's from the ground-based experiment. On the left panel, you will see the crater growing. And on the right panel, you will see two plots, the red dots for the volume, and then the triangular black dots are for the crater depth. Okay, I'll stop it here. The conical part is not seen here because it's all cloudy and dusty there. But one really interesting pattern we observed in this plot is that on the crater depth, even if the crater depth stops growing at about 4 seconds for this experiment, but if you look at the volume, it keeps growing. That means the erosion is even erosion is happening within the constant rate even after the depth is stopped growing. This is because the contributions from the diffusion-driven sharing. Now we move on to the experiment that were performed on the reduced gravity. Here we take the set that was performed for 250 to 300 micron sand. On the left, we see the plot for volume versus time at different gravities, and then gravities increasing from top to bottom. On the right, we see the similar plot for the depth. And as you can see here, as we go higher in the gravity, the erosion rates are decreasing. But one thing we need to notice here is that, for example, for two gravity levels here, the bottom two curves, they were supposed to be the same. There is a gap there, which comes from the experimental error. And then for that, we have a repeated experiment, and then we will try to minimize the errors from there. Similarly, we looked at the Martian simulant. Here, nothing out of ordinary. They all follow the hierarchy of the gravity, and then the constant increase of the erosion rate, as I explained in a couple slides ago, is also followed nicely here. Then finally, we looked at the Coarse Martian simulant. Here, there's one more unique feature that we observe here. As we go higher in the gravity, there is a clump. The erosion is also clumped in a band, and then the depth is also clumped in a band. This is because when we go higher than a certain point of the gravity level, there is no real distinctions. The erosion saturates. Now, after that, we went back and then tried to scale the gravity for the first set of data that we analyzed. So what I did here is that I scaled the volume with the square root of the gravity, and then try to fit with that with the functions here, a constant times log of b, another constant times the time plus 1. Here the parameters A has a unit of the volume divided by the square root of gravity, and then the B has a unit of the inverse of the time. As we can see here, the fit is not that great. The gravity scaling converges the data in some extent, but the uncertainty in the fit parameter indicates that there are other variables involved. So to get the real conversion, the real scaling of the erosion rate, the scaling of the gravity is not enough. We need to parameterize all the variables involved in the erosions. So with that, we have come up with some hypotheses. If we have to express the erosion rate on this function, then the parameter A, this is just a hypothesis, may be explained with those variables. On the numerator, we have density of the gas, the velocity of the gas, the size of the nodules, and then in the denominator, we have density of the sand, size of the particle, and the gravity. So if we can parameterize all these parameters individually, then only we can scale the erosion rate properly. Similarly, for the time, it's less known. This is just my idea here. We need to investigate more. So what we hope to do at the end of this work is to develop a complete comprehensive expressions that connects the physics that happens in the cratering experiment. And with that, we hope that it will help to calculate the effect of the space shuttle landing and support the scientific integrity. That is my conclusions. And if there are any questions, I'll be happy to answer. Thank you.
Thank you very much. In the interest of time, we'll move to the next presentation. We'll be able to answer questions in the discussion period.